Tonight I want to take you somewhere extraordinary yet deeply personal, a place where the very fabric of reality seems to respond to your presence, where the universe itself appears to notice when you're paying attention. It's late, I imagine, wherever you are. Perhaps you're lying in bed, the day's weight slowly lifting from your shoulders, or maybe you're settling into a comfortable chair, ready to let your mind wander into the mysteries of existence. I'm curious. Where in the world are you listening from tonight? What time is it there? Is it the deep of night? Or perhaps that gentle twilight hour when the world grows quiet? If you enjoy these journeys into the cosmic unknown, these peaceful explorations of reality's strangest corners, I'd love for you to join me on future travels. Consider subscribing or following along. Not because I'm asking you to, but because there are so many more mysteries waiting for us to explore together. So many more nights where we can drift through the universe's most beautiful puzzles. Tonight, we're going to explore something that might sound impossible at first. The idea that light somehow knows when you're watching it. It's a question that seems to belong more to philosophy or poetry than to physics, something you could easily dismiss as a misunderstanding of how science works. And yet, the more we look at it, the more quietly intriguing it becomes. This isn't about mysticism or supernatural forces, it's about what actually happens in laboratories around the world, what physicists have been observing for nearly a century now. Something so strange that even Einstein couldn't quite accept it at first. What if the act of observation, the simple fact of you looking at something, was not just a passive reception of information, but a quiet doorway into how the universe really works at its most fundamental level? You and I were about to embark on a journey that begins with something as simple as sunlight streaming through your window and ends in the deepest questions about consciousness, reality, and what it means to exist in a universe that seems to respond to our attention. We'll travel through time to dusty laboratories where scientists first noticed something wasn't quite right with light, through the mathematics that describe a reality far stranger than our everyday experience suggests, and into the ongoing mystery that keeps physicists awake at night, not with worry, but with wonder. The light from your screen right now, these photons carrying these words to your eyes, they're part of this mystery too. Every particle of light that has ever existed, from the first moments after the Big Bang to the gentle glow of stars millions of light years away, seems to follow rules that shouldn't make sense. Rules that suggest the universe is far more interconnected, far more responsive to observation than we ever imagined. And somehow, in ways we're still trying to understand, you're part of this cosmic conversation, this quiet dialogue between observer and observed that plays out every time light moves through space. Let's begin our journey in the most ordinary of places, with light itself, this thing we take for granted every day, this phenomenon that fills our world with color and warmth and visibility. Light travels from the sun, taking about 8 minutes to cross the vast emptiness of space, arriving at Earth with the same constancy it has maintained for billions of years. It bounces off objects, enters our eyes, creates the entire visual world we navigate through. So familiar, so ordinary, so seemingly simple. And yet, light carries within it one of the deepest mysteries in all of physics. A puzzle that emerges not from its behavior in the vastness of space, but from what happens when we try to watch it very, very closely. Imagine for a moment that you could shrink down, smaller than an atom, smaller than an electron, until you could watch individual particles of light, photons, as they travel through space. This is what physicists began to do, not literally of course, but through incredibly precise experiments designed to observe light at its most fundamental level. They expected to see something simple, either waves like ripples on water or particles like tiny bullets of energy. Light, they reasoned, had to be one or the other. It couldn't be both. That would be like saying something could be both a wave on the ocean and a grain of sand at the same time. It didn't make logical sense. But the universe, as we're discovering tonight, doesn't always conform to our logical expectations. When scientists first began these experiments in the early 20th century, they noticed something peculiar. When they weren't directly observing light's path, when they just let it travel through their experimental apparatus without trying to determine exactly where each photon went, light behaved like a wave. It created interference patterns, those beautiful alternating bands of light and dark that you might have seen in photographs of physics experiments. These patterns only make sense if light is spreading out like a wave, interfering with itself, creating regions where waves add together, and regions where they cancel out. This was strange enough, but then came the truly bewildering part. When scientists added detectors to observe which path individual photons took through their experiments, something changed. The interference patterns disappeared. Light stopped behaving like a wave and started behaving like particles, like discrete packets of energy following definite paths. It was as if light somehow knew it was being watched and changed its behavior accordingly. Not in a conscious way. We're not suggesting photons have minds or awareness, but in a fundamental, physical way that challenges our understanding of what observation means in the quantum world. You might be settling deeper into your pillow now, perhaps pulling your blanket a little closer, and I want you to know that this mystery we're exploring isn't meant to unsettle you. Instead, think of it as discovering that the universe is far more interesting, far more interconnected than we imagined. Every time you open your eyes, every time light from the world around you enters your vision, you're participating in this cosmic dance between observer and observed. You're not just passively receiving information about the world, in some deep physical sense that we're still trying to understand. You're participating in the creation of the reality you observe. The story of how we discovered this strange behavior of light begins in the early 1800s with a British physician named Thomas Young. Young was one of those remarkable individuals whose curiosity couldn't be contained by a single field. He studied medicine, yes, but he also made contributions to understanding Egyptian hieroglyphics, the mechanics of the eye, and the nature of light. On quiet evenings, much like this one, Young would conduct experiments in his study, using candles and cards with tiny holes and slits cut in them. Simple tools, but with them he would shake the foundations of physics. Young's most famous experiment, which we now call the double-slit experiment, was beautifully simple. He allowed light to pass through two narrow slits cut in a barrier, then observed the pattern that formed on a screen behind the slits. If light were made of particles, he reasoned, it should create two bright lines on the screen, corresponding to the two slits. But that's not what he saw. Instead, he observed a series of alternating bright and dark bands, an interference pattern that could only be explained if light were a wave, splitting at the two slits and then recombining, sometimes reinforcing itself, sometimes cancelling itself out. For over a century, this wave nature of light seemed settled. Light was a wave, like sound or water ripples, and that was that. But then came the quantum revolution of the early 1900s, when scientists like Max Planck and Albert Einstein showed that light also had to be made of particles, photons, to explain other phenomena like the photoelectric effect. Light, it seemed, was somehow both wave and particle, a duality that defied common sense, but accurately described experimental results. Now here's where our story takes its strangest turn. In the modern version of Young's double-slit experiment, scientists can send photons through the apparatus one at a time. Individual particles of light, separated by enough time that they couldn't possibly interact with each other. You would think that each photon, being a particle, would have to go through either one slit or the other, like a marble rolling through one of two doorways, and, if you accumulated enough individual photons, you'd expect to see two bright spots on the detector screen, corresponding to the two slits. But that's not what happens. Even when photons go through one at a time, over time they build up the same interference pattern that Young observed with continuous light. Each individual photon somehow interferes with itself, as if it goes through both slits simultaneously when we're not watching. It's as if each photon exists in what physicists call a superposition, a state of being in multiple places at once, taking all possible paths through the experiment until something causes it to choose a definite path. And what causes this choice? This is where you come in, where observation enters our story in the most profound way. When scientists place detectors at the slits to determine which path each photon takes, the interference pattern vanishes. The photons start behaving like simple particles, going through one slit or the other, never both. The mere act of observation, of gaining information about which path the photon took, fundamentally changes the outcome of the experiment. Perhaps you're wondering what exactly constitutes observation in this context. It's not about consciousness, at least not in the way we usually think about it. The detector doesn't need to be connected to a human observer. It doesn't require someone to actually look at the data. The key is information. Specifically, whether information about the photon's path is available in principle, whether it's encoded somewhere in the physical world. When such information exists, when there's a physical record of which slit the photon went through, the photon behaves like a particle. When no such information exists, when the photon's path remains fundamentally unknown and unknowable, it behaves like a wave. This brings us to one of the most beautiful and mysterious aspects of quantum mechanics, the idea that reality at its most fundamental level exists in a state of potential until the moment of measurement. Before observation, before the creation of information about a quantum system, that system exists in what physicists call a superposition of all possible states. The photon really does go through both slits. It's not that we don't know which slit it went through, it's that it genuinely went through both until something in the physical world forces it to have gone through just one. The mathematics that describes this, the equations of quantum mechanics, are among the most successful in all of science. They predict experimental results with extraordinary precision, allowing us to build technologies like lasers, computer chips, and MRI machines. And yet, the physical interpretation of these equations, what they tell us about the nature of reality, remains one of the deepest mysteries in physics. How can something be in multiple states at once? How does observation cause this superposition to collapse into a definite state? What exactly happens in that moment of transition from quantum potential to classical reality? These questions have occupied some of the greatest minds in physics for nearly a century. Niels Bohr, one of the founders of quantum mechanics, argued that we simply had to accept the wave-particle duality as a fundamental feature of nature, that our classical concepts of wave and particle were inadequate to describe quantum reality. Einstein, despite his crucial contributions to quantum theory, never fully accepted this view. He famously said that God does not play dice with the universe, expressing his discomfort with the seemingly random nature of quantum measurement. But experiment after experiment has confirmed the strange predictions of quantum mechanics, not just with photons, but with electrons, atoms, even large molecules containing thousands of atoms. They all exhibit this same bizarre behavior, acting like waves when unobserved, collapsing to particle-like behavior when measured. The boundary between the quantum world of superposition and the classical world of definite states remains fuzzy, but it seems to be related to how much a system interacts with its environment, how much information about it leaks into the surrounding world. You might be feeling drowsy now, your thoughts beginning to drift like particles in superposition, existing in multiple states of consciousness at once. That's perfectly fine. In fact, it's rather fitting. Your brain itself, some scientists speculate, might harness quantum effects in its operation, though this remains highly controversial. But whether or not quantum mechanics plays a role in consciousness, there's something poetic about contemplating these mysteries as you drift towards sleep, your awareness gradually becoming less focused, more distributed, more wave-like. Let's return to our central mystery. Why does light seem to know when you're watching it? The answer, as we've seen, lies not in light having knowledge or awareness, but in the fundamental nature of quantum reality. When we say light knows you're watching, what we really mean is that the act of observation, the physical interaction that creates information about a quantum system, fundamentally changes that system's behavior. It's not magic or mysticism, it's the way the universe works at its smallest scales. This leads us to consider what physicists call the measurement problem. In the mathematics of quantum mechanics, a quantum system evolves smoothly and predictably according to the Schrödinger equation, until the moment of measurement, when it suddenly and randomly collapses to a definite state. But what exactly constitutes a measurement? When does the collapse happen? Is it when the photon hits the detector? When the detector registers the hit? When the information is recorded? When a conscious observer looks at the record? These questions might seem abstract, but they touch on something profound about the nature of reality. They suggest that the universe we observe, the definite classical world of everyday experience, emerges from a more fundamental quantum reality through the process of observation and measurement. Every interaction, every exchange of information between quantum systems contributes to the emergence of the classical world we inhabit. Some physicists have proposed radical solutions to the measurement problem. Hugh Everett III suggested that the wave function never actually collapses. Instead, all possible outcomes of a measurement occur, each in its own parallel universe. In this many worlds interpretation, when you observe which slit a photon went through, the universe splits. In one universe, you observe it going through the left slit. In another universe, another version of you observes it going through the right slit. Both universes are equally real, equally valid. It's a mind-bending idea that transforms the measurement problem into a question about why we experience only one of these many worlds. Other interpretations suggest that consciousness itself plays a special role in collapsing the wave function, though this remains highly controversial and is not widely accepted among physicists. Still others propose that the collapse is a real physical process that happens spontaneously, caused by gravity or some other mechanism we don't yet understand. Each interpretation has its supporters and detractors, its strengths and weaknesses. The fact that we still don't have consensus on this fundamental question shows just how mysterious the quantum world remains. But perhaps the most remarkable thing about this mystery is that it doesn't prevent us from using quantum mechanics. Every day, billions of transistors in computer chips around the world operate according to quantum principles. Lasers in DVD players, fiber optic cables, and medical devices rely on the quantum nature of light. MRI machines in hospitals use quantum properties of atomic nuclei to create detailed images of the human body. We've built a technological civilization on quantum mechanics, even while we continue to puzzle over what it means. As you lie there, perhaps feeling yourself beginning to drift, consider the photons from your screen or lamp that are reaching your eyes right now. Each one has traveled its own path, but until it interacted with your retina, its path was not definite. It existed in a superposition of all possible paths, a ghostly probability wave spreading through space. Only in the moment of detection, when it triggered a chemical reaction in your eye, did its history become fixed, its path become real. In a very literal sense, your observation brought its specific history into being. This might seem to give us as observers a special status in the universe. But it's important to remember that observation in quantum mechanics doesn't require a conscious observer. Any physical interaction that creates information about a quantum system counts as an observation. A photon bouncing off a dust particle in space, an electron colliding with an atom, even the cosmic microwave background radiation interacting with particles. All of these are observations in the quantum mechanical sense. The universe is constantly observing itself, constantly collapsing quantum possibilities into classical realities. This process of decoherence, as physicists call it, is why we don't see quantum superposition in our everyday lives. Large objects like coffee cups and cats are constantly interacting with their environment, air molecules, photons, gravitational fields. These interactions rapidly destroy quantum superposition, forcing objects into definite classical states. It's only in carefully controlled laboratory conditions, or in the isolation of space, or at the scale of individual particles, that quantum superposition can persist long enough for us to observe its strange effects. The more we learn about quantum mechanics, the more we realize that the boundary between the observer and the observed is not as clear as we once thought. In quantum field theory, our most fundamental theory of particles and forces, even the vacuum of empty space is alive with quantum fluctuations, virtual particles popping into and out of existence, a constant foam of possibility at the smallest scales. We're not separate from this quantum world, watching it from outside. We're part of it, made of it, constantly participating in the cosmic process of observation and collapse that brings the classical world into being. This interconnectedness extends beyond just the observer and the observed. Quantum mechanics predicts, and experiments have confirmed, that particles that have interacted in the past can remain entangled, their properties correlated in ways that seem to defy our usual understanding of space and causation. Measure one particle of an entangled pair, and you instantly know something about its partner, no matter how far away it might be. Einstein called this spooky action at a distance, and thought it showed that quantum mechanics must be incomplete. But experiment after experiment has confirmed that entanglement is real, that the universe is non-local in a way that challenges our intuitions about separateness and distance. Perhaps this is why the question of whether light knows you're watching it resonates so deeply. It hints at a universe that is far more interconnected than we imagined, where the act of observation is not passive but participatory, where consciousness, or at least the physical processes that create information, plays a fundamental role in shaping reality. It's not that the universe is conscious or aware in the way we are, but rather that the distinction between observer and observed, between subject and object, is not as fundamental as we once believed. As we continue our journey deeper into this mystery, I want you to imagine yourself as part of this quantum dance. Every atom in your body, every electron orbiting every nucleus, is constantly engaging in quantum interactions. The very chemistry that powers your thoughts, the electrical signals traveling through your neurons, all of this emerges from quantum processes. You're not just an observer of the quantum world, you're a quantum system yourself, incredibly complex, constantly decohering and recohering, classical and quantum at the same time. The warmth you feel from your blanket comes from infrared photons emitted by the fabric, each one a quantum of electromagnetic energy. The sound of my voice, if you're listening rather than reading, arrives as pressure waves in the air, but those waves are made of countless air molecules, each following the laws of quantum mechanics. Even the sensation of lying on your bed emerges from electromagnetic forces between atoms, forces carried by virtual photons constantly exchange between electrons. At every scale, in every moment, you're immersed in the quantum world. Scientists have pushed the boundaries of quantum behavior to remarkable extremes. They've created quantum superpositions of objects large enough to see with the naked eye, though only barely. They've maintained quantum coherence in warm, wet environments like those found in living cells, suggesting that life itself might harness quantum effects. They've even begun to build quantum computers that exploit superposition and entanglement to perform calculations impossible for classical computers. These advances bring us closer to understanding the transition from quantum to classical, the process by which the strange becomes familiar, the multiple becomes singular. But they also deepen the mystery. If quantum effects can persist in warm biological systems, might they play a role in the emergence of consciousness? If quantum computers can maintain coherent superpositions of thousands of qubits, what does this tell us about the nature of information and reality? Some researchers have suggested that the brain might be a quantum computer of sorts, that consciousness emerges from quantum processes in microtubulars within neurons. This remains highly speculative and controversial, but it points to a fascinating possibility, that the mystery of consciousness and the mystery of quantum measurement might be related, two aspects of the same deep puzzle about the nature of reality and observation. Whether or not consciousness plays a special role in quantum mechanics, there's something profound about the fact that the universe has evolved creatures capable of observing and understanding it. Through us, the universe has developed the ability to observe itself, to collapse its own wave functions, to bring definite realities out of quantum possibilities. We're not separate from nature, watching it from outside. We're nature observing itself, quantum systems that have become complex enough to study quantum systems. This brings us to a philosophical question that has haunted physics since the early days of quantum mechanics. What is the role of the observer in physical theory? In classical physics, we could imagine the universe existing and evolving independently of observers. The planets would orbit the sun, atoms would vibrate, light would propagate through space, all without anyone watching. But quantum mechanics seems to suggest that observation is more fundamental, that the properties of quantum systems don't exist independently of measurement. This doesn't mean that the moon disappears when no one is looking at it, as Einstein sarcastically suggested. The moon is constantly being observed by sunlight, cosmic rays, gravitational interactions with Earth and other bodies. These interactions maintain its classical state, its definite position and momentum. But at the quantum level, for truly isolated systems, the question of what exists between observations remains open and mysterious. Different interpretations of quantum mechanics give different answers. In the Copenhagen interpretation, the most widely taught, though not necessarily the most widely believed, quantum properties simply don't exist between measurements. The wave function is just a tool for calculating probabilities, not a description of physical reality. In the many worlds interpretation, all possibilities exist simultaneously in parallel universes. In objective collapse theories, the wave function is real and collapses spontaneously according to some yet unknown physical process. Each interpretation has profound implications for our understanding of reality. If the Copenhagen interpretation is correct, then the universe is fundamentally probabilistic, with genuine randomness at its heart. If many worlds is correct, then everything that can happen does happen, somewhere in the vast multiverse. If objective collapse is correct, then there's new physics waiting to be discovered, a mechanism that bridges the quantum and classical worlds. But perhaps the most intriguing possibility is that we're asking the wrong questions. that our classical concepts of reality, observation, and existence are simply inadequate for understanding the quantum world. Just as relativity showed us that space and time are not absolute but depend on the observer's motion, quantum mechanics might be showing us that reality itself is not absolute but depends on observation and measurement. This observer dependence of reality extends beyond just quantum mechanics. In relativity, different observers disagree about the simultaneity of events, about the rate at which time passes, about the length of objects and the mass of particles. There's no absolute frame of reference, no God's eye view of the universe. Each observer has their own valid perspective, their own slice through space-time, their own version of now. Combining quantum mechanics with relativity leads to quantum field theory, our most fundamental description of particles and forces. In this framework, even the number of particles in the universe is observer-dependent. An accelerating observer sees particles where an inertial observer sees only vacuum. The Unruh effect, as this is called, shows that even the distinction between something and nothing depends on who's looking. These ideas might seem abstract, far removed from your experience as you lie there in the darkness, but they speak to something deep about the nature of existence. The universe is not a fixed stage on which we act out our lives. It's a participatory phenomenon, shaped by observation, influenced by measurement, brought into being through the constant interaction of its parts. You're not just in the universe, you're part of the process by which the universe defines itself. As you feel yourself growing more drowsy, your thoughts becoming less focused, consider that you might be experiencing something analogous to quantum superposition. In the drowsy state between waking and sleeping, thoughts and images blend and merge, multiple possibilities coexist, the boundaries between self and world become fuzzy. It's only when you focus your attention, when you observe a particular thought, that it becomes definite and clear. The rest remains in a kind of mental superposition, potential thoughts waiting to be actualized. This parallel between consciousness and quantum mechanics, while speculative, points to something interesting about the nature of observation. In both cases, the transition from multiple possibilities to a single actuality seems to require some kind of selection, some process that picks out one option from many. In quantum mechanics, we call this wave function collapse. In consciousness, we might call it attention or awareness. Whether these are related or merely analogous remains an open question. The mystery deepens when we consider time. In the equations of quantum mechanics, time plays a special role. Unlike position or momentum, which can be in superposition, time is always definite, always classical. The wave function evolves through time, but time itself doesn't have a wave function. This asymmetry between time and space in quantum mechanics is puzzling and might hold clues to understanding the measurement problem. Some physicists have suggested that the flow of time itself might emerge from quantum measurement, that the arrow of time, the fact that we remember the past but not the future, is related to the irreversibility of wave function collapse. Each observation, each measurement, each bit of information created in the universe adds to its entropy, driving time forward. In this view, time doesn't flow independently of events. It emerges from them, from the constant process of quantum systems observing each other. This would mean that you, right now, through the simple act of existing and interacting with your environment, are participating in the creation of time itself. Every breath you take, every heartbeat, every neural firing in your brain is a quantum event that contributes to the arrow of time. You're not just moving through time, you're helping to create it, to give it direction and meaning. The photons from distant stars reaching your eyes have traveled for years, centuries, millennia to get here. During their journey through the vacuum of space, they existed in superposition, their paths undefined, their properties uncertain. Only now, in the moment they interact with your retina, does their history become fixed. In a sense, your observation reaches back through time, collapsing possibilities that existed long before you were born. The past is not fixed and immutable. It's created in the present through the act of observation. This retroactive collapse of the wave function has been demonstrated experimentally in what physicists call delayed choice experiments. By choosing whether or not to observe which path a photon took through an apparatus, even after the photon has already passed through, experimenters can retroactively determine whether the photon behaved as a wave or a particle. It's as if the photon's history depends on a future choice, as if causation can run backward through time at the quantum level. Such experiments challenge our usual notions of cause and effect of past and future. They suggest that the universe is not a deterministic machine, grinding forward from past to future according to fixed laws. Instead, it's a more fluid, probabilistic entity, where past, present, and future are interconnected in ways we're only beginning to understand. The universe's history is not written in stone. It's constantly being written and rewritten through the ongoing process of observation and measurement. As we approach the halfway point of our journey tonight, let's pause and reflect on what we've discovered. Light, this most familiar of phenomena, harbors one of the deepest mysteries in physics. When unobserved, it behaves as a wave, spreading out through space, interfering with itself, existing in multiple states simultaneously. When observed, it behaves as a particle, following definite paths, having specific properties. This wave-particle duality is not unique to light. It's a fundamental feature of all quantum objects, from electrons to atoms to molecules. The transition from wave to particle, from superposition to definite state, happens through observation. But observation doesn't require consciousness. It only requires physical interaction that creates information. The universe is constantly observing itself, constantly collapsing quantum possibilities into classical realities. We're part of this process, not separate from it. Every interaction we have with the world around us is an act of mutual observation, a dance of measurement and collapse that brings reality into being. This participatory universe, where observation plays a fundamental role, challenges our classical notion of an objective reality existing independently of observers. Different interpretations of quantum mechanics offer different resolutions to this challenge, from parallel universes to conscious collapse to new physics yet to be discovered. We don't yet know which interpretation is correct, or whether the true answer is something we haven't thought of yet. What we do know is that quantum mechanics works. It describes the world with extraordinary precision and has enabled technologies that would seem like magic to earlier generations. It tells us that the universe is far stranger than our everyday experience suggests, that reality at its most fundamental level operates according to rules that defy common sense. And it suggests that we, as observers, play a more important role in the cosmos than we might have imagined. The gentle hum of electronics around you, the soft glow of LED lights, the warmth of your electric blanket if you have one, all of these depend on quantum mechanics. The semiconductors in computer chips, the lasers in fiber optic cables, the superconductors in MRI machines. None of these would work if the quantum world behaved according to classical rules. Our modern technological civilization is built on quantum weirdness, on the wave-particle duality that seems so counterintuitive. Even biological systems might harness quantum effects. Photosynthesis, the process by which plants convert sunlight into chemical energy, appears to use quantum coherence to efficiently transport energy through protein complexes. Some birds might navigate using quantum entanglement in certain proteins in their eyes, allowing them to sense Earth's magnetic field. Even human vision relies on the quantum mechanical absorption of photons by rhodopsin molecules in our retinas. As you lie there, perhaps feeling your eyelids growing heavier, consider that the boundary between the quantum and classical worlds might not be as sharp as we once thought. Quantum effects might persist in warm, wet, noisy environments like living cells. The transition from quantum to classical might be gradual rather than sudden, with different degrees of quantumness possible. We might live in a world that is classical at large scales but quantum at small scales, with a fuzzy boundary in between where both descriptions partially apply. This fuzzy boundary is where some of the most interesting physics happens. It's where researchers are pushing the limits of quantum behavior, creating larger and larger quantum superpositions, maintaining quantum coherence for longer and longer times. They're exploring the mesoscopic realm, the middle ground between the microscopic and macroscopic, where quantum and classical physics meet and merge. In this realm, we find phenomena that seem almost magical, superfluids that flow without friction, climbing up the walls of their containers, defying gravity. Superconductors that carry electricity without resistance, maintaining currents for years without any power source. Bose-Einstein condensates where thousands of atoms merge into a single quantum state, behaving as one giant matter wave. These are not abstract theoretical predictions. They're real phenomena that scientists create and study in laboratories around the world. The fact that such exotic states of matter can exist, that quantum mechanics allows for such strange and wonderful phenomena, tells us something profound about the universe. It's not just a collection of particles interacting according to fixed rules. It's a rich, complex, multi-layered reality where the impossible becomes possible, where the rules themselves depend on the scale and context, where observation and existence are intimately intertwined. Let's return once more to our central question. Why does light seem to know when you're watching it? We've seen that this knowledge is not conscious awareness, but rather a fundamental feature of quantum mechanics. The act of observation, of measurement, of creating information about a quantum system necessarily disturbs that system, forcing it from superposition into a definite state. This is not a flaw in our measuring devices. It's a fundamental principle of nature encoded in the mathematics of quantum mechanics. The uncertainty principle, formulated by Werner Heisenberg, tells us that we cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely we measure one, the less precisely we can know the other. This is not due to experimental limitations, it's a fundamental property of quantum systems. The information simply doesn't exist. A particle doesn't have both a definite position and a definite momentum. It has what physicists call complementary properties that cannot be simultaneously well defined. This complementarity extends beyond position and momentum to wave and particle properties, to energy and time, to various other pairs of observables. It tells us that the quantum world is fundamentally different from the classical world of our everyday experience. We cannot have complete information about a quantum system. We must choose what to measure, what to know, and our choice affects what the system becomes. In choosing to measure which slit a photon passes through, we gain information about its particle nature, but lose information about its wave nature. The interference pattern, which depends on the photon passing through both slits as a wave, disappears. We've traded one kind of information for another, and in doing so we've influenced what the photon is, how it behaves, what properties it manifests. This trade-off between different kinds of information, this complementarity of quantum properties, might extend beyond physics into other realms. Some researchers have suggested that there might be complementarity in biology, in neuroscience, even in psychology. Perhaps certain aspects of living systems, of consciousness, of human experience are complementary in the quantum mechanical sense. We can understand one aspect or another, but not all simultaneously. The mystery of why light knows you're watching it thus connects to broader mysteries about information, observation, and reality. It suggests that information is not just an abstract concept, but a physical quantity, as real as energy or momentum. The creation, processing, and destruction of information are physical processes that obey physical laws. And the relationship between information and observation, between knowledge and reality, lies at the heart of quantum mechanics. In recent decades, this connection between quantum mechanics and information has led to the development of quantum information theory, a new field that explores how information behaves in the quantum realm. Quantum information is fundamentally different from classical information. It can exist in superposition, be entangled across space, and cannot be copied perfectly. The no-cloning theorem tells us that we cannot make an exact copy of an unknown quantum state. These properties of quantum information have profound implications. They enable quantum cryptography, where the security of communication is guaranteed by the laws of physics. Any eavesdropper trying to intercept a quantum message necessarily disturbs it, alerting the sender and receiver to their presence. They enable quantum teleportation, where the quantum state of one particle can be transferred to another distant particle using entanglement and classical communication, and they enable quantum computation, where quantum superposition and entanglement allow for algorithms that would be impossible on classical computers. The development of quantum computers is particularly fascinating in the context of our discussion tonight. These machines exploit the very phenomenon we've been exploring, the ability of quantum systems to exist in superposition until observed. A quantum computer's qubits can be in superposition of 0 and 1, allowing the computer to explore multiple computational paths simultaneously. Only when the computation is complete and the result is measured does the superposition collapse to a definite answer. In a sense, a quantum computer is a device for harnessing the universe's ability to explore multiple possibilities simultaneously. It's a way of using the quantum nature of reality to solve problems that would be intractable for classical computers. And it relies crucially on maintaining quantum coherence, on preventing unwanted observations from collapsing the superposition too early. The challenge of building quantum computers is largely the challenge of isolation, keeping the qubits from being observed by their environment until the computation is complete. This brings us to an interesting perspective on the role of observation in quantum mechanics. Rather than seeing observation as a limitation, as something that destroys quantum superposition, we can see it as a resource, as the mechanism by which quantum possibilities become classical realities, by which information is created and processed. The interplay between coherence and decoherence, between superposition and collapse, between quantum and classical, is what allows for the richness and complexity of the universe we inhabit. As you drift closer to sleep, your consciousness flickering between waking and dreaming, consider that you might be experiencing your own version of quantum superposition and collapse. In the drowsy state, multiple thoughts and images coexist, blend, interfere with each other. Your attention, like a measurement device, selects certain thoughts, brings them into focus, collapses them into definite experiences. The rest fade back into the quantum-like fuzz of potential thoughts, waiting for another moment of attention to bring them to life. This analogy between consciousness and quantum mechanics, while imperfect, points to something deep about the nature of observation and experience. Both involve the selection of specific outcomes from a field of possibilities. Both involve the creation of definite states from indefinite potentials. Both involve a kind of interaction between observer and observed that changes both parties. Whether this is mere analogy or points to a deeper connection remains one of the great mysteries of science and philosophy. The question of consciousness and its relationship to quantum mechanics brings us to the edge of known science. Some researchers, like Roger Penrose and Stuart Hameroff, have proposed that consciousness emerges from quantum processes in microtubules within brain cells. They suggest that the collapse of the wave function is not random but is influenced by a quantum gravity effect that gives rise to conscious experience. This remains highly controversial and is not widely accepted, but it represents a serious attempt to bridge the gap between the physical and the mental, between the objective and the subjective. Other researchers approach the question from the opposite direction, suggesting that consciousness might be fundamental to the universe, that observation in the quantum mechanical sense might require some primitive form of experience or awareness. This view, known as panpsychism, is ancient in philosophy, but has recently gained renewed interest as a potential solution to both the hard problem of consciousness and the measurement problem in quantum mechanics. Whether or not consciousness plays a special role in quantum mechanics, there's something remarkable about the fact that we can even ask these questions. The universe has evolved creatures capable of observing and understanding it, of discovering its quantum nature, of building devices that exploit quantum phenomena. Through us, the universe has become self-aware, able to observe itself, to collapse its own wave functions, to ponder its own mysteries. We are, in a very real sense, the universe's way of observing itself. Every measurement we make, every observation, every bit of information we create contributes to the ongoing process by which quantum possibilities become classical realities. We're not separate from nature, watching it from outside. We're part of the cosmic observation process, participants in the great dance of measurement and collapse that has been going on since the beginning of time. And what a dance it is! From the first moments after the Big Bang, when quantum fluctuations in the primordial plasma seeded the formation of galaxies, to the nuclear fusion in stars where quantum tunneling allows protons to overcome their mutual repulsion, to the chemical reactions in your cells right now where electron clouds merge and separate in quantum mechanical ways. The entire history of the universe is a history of quantum processes becoming classical through observation and interaction. The cosmic microwave background radiation, that faint echo of the Big Bang that fills all of space, carries the imprint of quantum fluctuations from the universe's earliest moments. These tiny variations in temperature, just parts per million, arose from quantum uncertainty in the infant universe. Through gravitational collapse over billions of years, these quantum fluctuations grew into the galaxies, stars, and planets we see today. The large-scale structure of the universe, the cosmic web of galaxy clusters and voids, All of it traces back to quantum mechanics in the first fraction of a second after the Big Bang. Even the elements that make up your body have a quantum origin. The carbon in your cells, the oxygen you breathe, the iron in your blood, all were forged in the hearts of stars through quantum mechanical processes. When massive stars exploded as supernovae, scattering these elements across space, it was quantum mechanics that determined the nuclear reactions, the energy release, the creation of elements heavier than iron in those final violent moments. And now, billions of years later, these star-forged atoms have assembled into you, a conscious being capable of observing and understanding the universe. The photons entering your eyes right now might have traveled for millions of years from distant stars, existing in quantum superposition until the moment they interact with the rhodopsin molecules in your retina. In observing them, you're participating in a cosmic process that connects you to the entire history of the universe. As we enter the final phase of our journey tonight, let's explore some of the more speculative and philosophical implications of quantum observation. If observation plays such a fundamental role in quantum mechanics, what does this mean for our understanding of reality? Is there an objective reality independent of observation, or is reality somehow created through the act of observation? Different physicists and philosophers give different answers to these questions. The physicist John Wheeler proposed that we live in a participatory universe, where observers are necessary to bring the universe into being. He imagined the universe as a self-excited circuit, observing itself into existence through the emergence of observers. In this view, the universe is not a machine grinding out predetermined outcomes, but a participatory phenomenon where observation plays a creative role. Others, like the physicist David Deutsch, argue for a many-worlds interpretation where all possible outcomes of quantum measurements occur in parallel universes. In this view, observation doesn't collapse the wave function, it entangles the observer with the observed system. When you observe which slit a photon went through, you don't cause it to choose one path or the other. Instead, you split into multiple versions of yourself, each observing a different outcome in a different branch of the multiverse. Still others seek a middle ground, proposing that there is an objective quantum reality described by the wave function, but that this reality is very different from our classical intuitions. The wave function is not just a calculational tool, but a real entity that exists in an abstract mathematical space called Hilbert space. Observation causes the wave function to collapse, but this collapse is an objective physical process, not dependent on consciousness or awareness. These different interpretations have different implications for free will, determinism, and the nature of choice. In some interpretations, the randomness of quantum measurement introduces genuine indeterminacy into the universe, creating room for free will. In others, like many worlds, everything is deterministic from a bird's-eye view of the multiverse, though it appears random from our limited perspective within one branch. The relationship between quantum mechanics and free will remains an open and actively debated question. But perhaps these philosophical questions, while fascinating, miss something important about the practical reality of quantum observation. Whatever the ultimate nature of reality, the fact remains that quantum mechanics works. It describes the world with extraordinary precision, enables amazing technologies, and reveals deep truths about the universe. The mystery of observation, rather than being a problem to be solved, might be a fundamental feature of reality, something to be accepted and explored rather than explained away. As you lie there, perhaps on the edge of sleep now, consider that the mystery of why light knows you're watching it is really the mystery of existence itself. It's the mystery of how the possible becomes actual, how potential becomes real, how the quantum becomes classical. It's a mystery that plays out every moment, in every interaction, in every observation. You're not just learning about this mystery, you're living it, embodying it, participating in it with every breath, every heartbeat, every thought. The room around you seems solid and definite, but at the quantum level, it's a seething foam of virtual particles, quantum fluctuations, probability waves. The atoms in the walls, the molecules in the air, even the photons carrying the image of these words to your eyes, all of them exist in a constant dance between quantum and classical, between wave and particle, between potential and actual. And you, through your presence, through your observations, are part of what makes it real, what gives it definite form. This is not to say that you create reality through wishful thinking, or that consciousness magically affects the physical world. The collapse of the wave function follows precise mathematical rules, obeys conservation laws, respects the fundamental symmetries of nature. but it does mean that observation, measurement, the creation of information, these are not passive acts of discovery but active processes that participate in the becoming of reality. In quantum field theory, even the vacuum is not empty but filled with quantum fluctuations, virtual particles that pop into and out of existence, borrowing energy from the future and paying it back before the universe notices. These fluctuations are not just theoretical abstractions, they have measurable effects. The Casimir effect, where two metal plates in vacuum are pushed together by quantum fluctuations, has been measured in laboratories. The Lamb shift in hydrogen atoms, caused by virtual photons, can be calculated to extraordinary precision. These quantum fluctuations in the vacuum might even be related to dark energy, the mysterious force that's causing the expansion of the universe to accelerate. If so, then the quantum nature of reality is not just a microscopic curiosity, but a cosmic force shaping the evolution and fate of the universe. The same quantum principles that govern the behavior of light in the double-slit experiment might also govern the ultimate destiny of all existence. As we near the end of our exploration, let's return once more to the simple yet profound question that started our journey. Why does light seem to know when you're watching it? We've seen that this apparent knowledge is not consciousness or awareness, but a fundamental feature of quantum mechanics. Observation necessarily affects the observed, not through any mystical influence, but through the physical process of measurement, the creation of information, the interaction between quantum systems. We've explored how this principle extends beyond just light to all quantum systems, from electrons to atoms to molecules. We've seen how the wave-particle duality, the superposition of states, the collapse of the wave function, are all aspects of a deeper quantum reality that underlies our classical world. We've considered different interpretations of what this means, from parallel universes to participatory creation to objective collapse. We've discovered that we ourselves are quantum systems, that observation and measurement are not things we do to the universe, but processes we participate in as part of the universe. Every interaction, every exchange of information, every moment of experience is a quantum event where possibilities become actualities, where the quantum becomes classical, where the universe observes itself into being. The mystery of quantum observation connects to the deepest questions in physics and philosophy. What is the nature of reality? What is the role of information in the physical world? How does the classical world emerge from the quantum? What is the relationship between observer and observed? These questions remain open, actively researched, passionately debated. The fact that we don't have final answers, that mystery remains at the heart of our most successful physical theory, is not a failure but an invitation to continued wonder and exploration. As your thoughts begin to dissolve into the gentle chaos of approaching sleep, consider that you're experiencing something not entirely unlike quantum superposition. Your consciousness is becoming less focused, more distributed. Multiple thoughts and images coexist without conflict. The boundaries between self and world, between real and imagined, between possible and actual, begin to blur. In dreams, you might experience something like the many worlds interpretation, where contradictory realities coexist, where you can be in multiple places at once, where the laws of classical physics need not apply, and when you wake tomorrow, your consciousness will collapse back into classical definiteness, selecting one thread of experience from the quantum foam of possibilities. You'll open your eyes, and photons will collapse from their superposition states, bringing you information about the world. You'll observe, and in observing, you'll participate in the endless process by which the universe defines itself, moment by moment, observation by observation. The photons from the morning sun will have traveled 8 minutes through space, existing in superposition until they interact with your retina. The light from your lamp or screen will have crossed the room in nanoseconds, its path undefined until observed. Every photon, every particle, every quantum of energy that reaches you will collapse from possibility to actuality through the simple fact of interaction, of observation, of information exchange. This is the quiet miracle that happens every moment of every day, usually without our notice or appreciation. The universe is constantly observing itself, constantly choosing what to become from an infinite sea of possibilities. And we, as conscious observers capable of understanding this process, have the privilege of watching it happen, of participating in it, of being it. So as you drift off to sleep tonight, remember that you're not separate from the cosmic mystery we've been exploring. You're part of it, an expression of it, a way for the universe to observe and know itself. Every observation you make, every bit of information you create, every interaction you have with the world around you, is a participation in the fundamental process by which reality emerges from possibility. The question of why light knows you're watching it is really the question of why anything exists in definite form rather than eternal superposition. And the answer, as far as we currently understand it, is that observation, measurement, information, these are not secondary aspects of reality but fundamental to it. The universe is not just made of matter and energy, but also of observation and information, of the constant process of quantum possibilities becoming classical realities. Perhaps this is why the mystery resonates so deeply with us. It suggests that we're not passive observers of a predetermined universe, but active participants in its ongoing creation. Not in a mystical or supernatural sense, but in a precise, mathematical, quantum, mechanical sense. Every observation matters, every measurement contributes, every bit of information adds to the growing, evolving, self-observing structure of reality. The universe knows you're watching because in a very real sense, the universe is watching through you. You're its eyes, its measurement devices, its way of collapsing quantum possibilities into classical realities. You're not separate from the cosmic process of observation. You're an integral part of it, a crucial component in the universe's ability to observe and define itself. And with that thought, as your eyes grow heavy and your mind begins to drift into the quantum superposition of dreams, remember that even in sleep, you remain part of this cosmic dance. Your atoms continue their quantum interactions, your electrons continue to collapse wave functions, your very existence continues to participate in the universal process of observation and creation. The mystery of why light knows you're watching it is ultimately the mystery of existence itself, of how something emerges from nothing, of how the definite emerges from the indefinite, of how the universe observes itself into being. It's a mystery that science has partially unveiled but not fully explained, a question that leads to ever deeper questions, a wonder that grows rather than diminishes with understanding. And as you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries gently, peacefully into the night. The photons continue their journeys through space. The quantum waves continue their superposition dance. The universe continues its self-observation, its self-creation, its endless becoming. And you, in your sleep, remain a part of it all, a quantum system among quantum systems, an observer even in dreams, a participant in the cosmic mystery of existence. Sweet dreams, fellow observer. May your sleep be filled with quantum possibilities, and may you wake to collapse them into beautiful realities. The universe will be watching, through you, with you, as you. Always and forever, in the endless dance of observation and existence, of light and awareness, of the quantum and the classical merged in the mystery of being. End.